Hello everyone, I'm Shimon Yu from Georgia Tech. It's my great pleasure to join the ESSCIRC and ESSCIRC virtual educational event. Today I'm going to discuss the computing memory technologies for deep learning accelerator, and I will focus on the chip prototyping, benchmark, and monolithic 3D integration. Here are the motivations to develop the specialized hardware accelerators for artificial intelligence or machine learning workloads. As we know, GPU is still dominating the training in the cloud, and we see that FPGA is becoming a popular platform for the inference, especially for fast prototyping. And also, there's a new trend to develop the digital ASIC platforms, for example, the Google's TPU, to perform the accelerations at the cloud as well as the edge. So if you look at the different computing platforms, the energy efficiency varies or not. So here the energy efficiency is using the metric tera operations per second per watt, or TOPS per watt. And the conventional computing platforms like GPU is about 0.1 TOPS per watt, but it can support the floating point computation. And the digital ASIC platforms like TPU or the equivalents can achieve like 1 to 10 TOPS per watt. But it can support the fixed point computation. If we want to further increase the energy efficiency to like 10 to 100 TOPS per watt, we believe that computing memory technology is a promising paradigm. So here we are going to use the analog computation within the memory array. The memory can be CMOS, like SRAM, or the emerging non-volatile memories. And then we have to embrace the low precision computation. And then the question is, can we achieve the same accuracy as the digital platforms? We are going to discuss those issues in the presentations today. Let's take a look at the difference between the conventional digital ASIC accelerators as shown on the left versus the computing memory accelerators shown on the right. So the difference is that in the conventional accelerators, still both the weights and the activations are shared in the global buffer, like the SRAM cache. And there are multiple processing elements made of the digital multipliers and adders. And then we are going to load in the activations and weights to do the MAC operations on the PEs. So still the computation happens within the PE, and the memory is separately stored on the global buffer. If you consider the computing memory approach, where the memories will store the weights, and then we only need to load in the activations into the memory macro. And then we just move around the input and output activations, and then we can save the data movement in the data flow. And also we may enable the parallel computations within the memory array. We are going to discuss that in more details the next slide. So overall, the energy efficiency of the computing memory will be significantly improved, and also the throughput may be also boosted. Here is a closer look at one subarray of the computing memory paradigm. So here we show the memory arrays in the rows and columns, where each cross point here represents a memory cell. So the memory cell can be either like 6 transistor SRAM bit cell, or like 1 transistor, 1 resistor RRAM cell. And here we can load in the input activations in parallel by activating multiple word lines, and then the voltage from the word line will activate the cell, and then we will get the current from the bit lines, and then we can sum up the current along the bit line. So here the summation is done by the bit line current accumulation. At the end of the column, we may need the marks to switch between columns, and then we may have the analog to digital converters like ADCs to convert the analog output to the digital. And then, depending on the precision of the weights, we may have to shift and add different columns due to the different significance. So this is a general scheme for the mixed signal computation, where the memory core performs the analog computation, and then we use the ADC as edge to digitize. Here is the outline of today's presentation. First, we will go through the SRAM-based designs, and then we move to the RRAM-based designs, and then we will present DNN+Neuro Sim benchmark framework, and then we will discuss general challenges in the chip design, and then lastly we will point out the future trend to have the Monolithic 3D integration to enable the computing memory with better area and throughput efficiency. Okay, why SRAM for computing memory? We know SRAM is a mature silicon CMOS technology that scales with logic process. SRAM is available today at 5 nanometer, and large capacity SRAM cache has been demonstrated. Here we show many variants of the SRAM bit cell that are proposed for computing memory. Let's consider the weak pattern stored in those bit cells like this. And then we look at the first one, conventional 60 bit cell. We can pre-charge both bit line, bit and bar with VDD, and then we can turn on multiple rows. Depending on the input activation, for example 1, in this case, we can turn on this word line. So there will be large discharge current from the bit line and small discharge current from the bit line bar. So we can sense the difference between those two bit lines to do the computation. If we want to further increase the difference between those two currents, we can use this split 60 bit cell as shown in the next. So here we can use word line and word line bar to independently control those two cascades. So this is essentially the XNOR computation. For example, in this case, only the bit line will have the discharge current. So the dynamic sense margin will be increased between the bit line and bit line bar. There's one potential issue with those 6 transistor SRAM cell, that is the rate disturb. When the bit line decays, then the storage node may be disturbed. To solve this issue, we can use the AT rate decoupled cell. So here we can add 2 additional cascades to do the readout process. So in this example, we can turn on the read word line by the input activation 1. Because this data pattern, you see the Q is 0, so the discharge path is disabled. But if we reverse the data pattern like this, then the 2 cascades will be turned on, then there will be discharge current from the bit line. So this is not going to impact the data stored on the storage node, and this is better in terms of the immunity to the rate disturb. And lastly, we sometimes need the transpose readout, especially for the training process. So we can have this transposable 8 transistor cell. So in the feed-forward process, then the operation is similar as the 6T conventional bit cell. But in the backward process, we are going to input the activation from the column side, and then we can read out from the horizontal side using those 2 additional cascades as shown on the figure. Now let's review a few representative works. This one was published at ISSCC 2018, and this is a split 60 SRAM bit cell using the Foundry's compact design rule, and this was taped out at 65 nanometer CMOS node. This work can support the XNOR net, essentially 1 bit input and 1 bit wait, and the measured energy efficiency is about 55 TOPS per watt. This is an improved design published at ISSCC 2019. So the design is to support multi-bit MAC operations. The key idea is to use this twin AT SRAM bit cell, where we have MSB AT cell and LSB AT cell. So the trick is to size up the W over L of those two passgates of the MSB cell. So the current will be twice as the LSB cell when the discharge happens along the bit line. And the input precision is encoded by the word line voltage. The measured energy efficiency at this 55 nanometer test chip can reach up to 90 TOPS per watt, depending on the precision. The same group published at ISSCC 2020 a new design to support the bidirectional access. So the design is based on regular 60 cells plus transposable computing cell. It can support both feed-forward, backward propagations for inference and training. And also multi-bit precision are supported, and the measured energy efficiency can be up to 60 TOPS per watt. So this design was implemented at 28 nanometer, and then with the FPGA as a control, the training accuracy for CIFAR 10 and 100 are reported here with reasonably good accuracy. Also at ISSCC 2020, TSMC reported a 7 nanometer computing memory design using 80 rate decoupled foundry cell. And also multi-bit precisions are supported, and the key idea here is to use analog shift and add to accumulate the significance from different cordons using a capacitor array. And the measured efficiency is very impressive. More than 300 TOPS per watt was reported, largely because of the very scaled technology. Let's have a brief summary. SRAM is a mature candidate for computing memory with state-of-the-art availability at 5 nanometer or beyond. Impressive energy efficiency has been reported, but the leakage power will be the main disadvantage for large capacity SRAM array, as SRAM is always leaking even in the standby mode. 6 transistor SRAM bit cell is the most compact, but it is suffered from the rate disturb when multiple rows are activated. Lowering the word line voltage will help, but still the maximum number of word lines that can be turned on simultaneously is very limited. 8 transistor SRAM bit cell can decouple the read and write paths, thus offer more flexibility in the design. Foundries typically offer 60 or 80 SRAM compact design rule, but if we want to further change the bit cell to add more routing, bit names, word names, then we need to use logic design rule that is handcrafted, which will have much larger cell layouts. In the older technology node, for example 65 nanometer, there are many rooms to modify the bit cell and reroute the interconnects. But in advanced node, for example 28 nanometer or beyond, foundry typically will not allow to change the bit cells. Okay, now let's move on to the RRAM-based design. Okay, why RRAM? For computing memory. RRAM is short for resistive random access memory, which is one of the emerging non-volatile memories. And the RRAM structure is very simple, with 2 electrodes and an oxide layer in between. So the RRAM essentially is a variable resistor, where the resistance can be tuned by the voltages you apply. So we can encode the weights into the conductance of the device. The benefits of RRAM compared to the SRAM include the following. First, much smaller cell size and possibly multi-bit per cell at the same technology node. That means we can potentially hold most of the weights on chip if we use a compact RRAM cells. As a reference, the deep neural network models typically need like more than 100 megabytes for storing the parameters today. So if we can hold all the weights on chip, we can eliminate or reduce off-chip DRAM access. And also, RRAM is a non-volatile memory, which means we can power off the chip in the standby mode. So there's almost no leakage for the dynamic power gating, and it can enable the instant on and off operations, which are very useful for the inference at the edge. And RRAM is backend of the NAND compatible, so we can potentially stacking the RRAM on top of each other for 3D integration. RRAM technology today is becoming technologically mature with foundry availabilities. So here we show some examples. For example, TSMC is offering 40nm RRAM process, and Intel also reported the 22nm RRAM process as well. And there are many other RRAM vendors in the field. For example, Wenbang from Taiwan, and Sony and Panasonic from Japan. Let's also review some of the recent progress in the RRAM-based designs. So this design was implemented at 90nm Wenbang's hafnium oxide RRAM technology, and the array can support the simultaneously turn on of all the rows, compared to the prior work, which can only turn on 9 rows at one time. This one can achieve much better throughput. For example, here you see the throughput can be like 20 times higher. If you consider the energy efficiency times the throughput, which is essentially the energy delay product, this design is like 10 times better than the prior design based on the RRAM technology. And the reasonably good accuracy was reported by this design. We will see more details in the next slide. One of the key features is the 2T2R bit cell. Here we use complementary VRLAM to represent the binary inputs and complementary RRAM states to represent the binary weights. Essentially, we can support the XNOR computation. As shown in this truth table, the bitwise XNOR output is represented by the effective resistance attached to the bit line. And here, the current summation can modulate the node voltage, where we will use a multi-level sense amplifier, essentially Flash ADC, to digitize this voltage. And the equivalent of the array is shown in this box, where we have a pull-down network modulated by the input voltage and the RRAM resistance, and then we have a PMOS pull-up. So by configuring the strength of the PMOS pull-up, we can have this kind of a transfer voltage curve between the bit line voltage here versus the bit count value of the input and the weight product. As we mentioned earlier, RRAM can store multi-level per cell. In this work, we experimentally demonstrated 2-bit RRAM from the same test chip as we showed in the previous slide. This plot shows the distribution of the 4 conductance levels. We use a very aggressive write and verify programming protocol to tighten the distribution, as shown in the black curve here. But as time goes by, the distribution tends to spread out. This is due to the relaxation effect of the RRAM states. But still, even after 108 hours, we retest the accuracy for the inference. Still, good accuracy can be expected. With this scheme, we can further improve the energy efficiency almost twice as the 1 bit per cell design in the previous slide. Let's have a quick summary for RRAM-based computing memory. We see 1T1R or 2T2R is a typical bit cell for RRAM-based computing memory. The cell area typically ranges from 30F² to 60F², which is about 2.5x to 5x higher density than the SRAM bit cell at the same technology node. But RRAM can store multi-level per cell, although the multi-level cell reliability needs further optimization. For example, we see the relaxation effect after the programming, and also the drift of the resistance or data retention at higher temperature needs further characterization, especially for the intermediate states. RRAM technology generally faces challenges of high programming voltage, especially in the forming process. and the low on-state resistance. We will discuss more in the later slides. Typically, iterative read verify is needed for accurately programming the resistance states. This is doable for the inference-only design because we just need one-time programming, but may be challenging for the in-situ training. RRAM scaling lags behind SRAM. State-of-the-art RRAM is available at 22 nm, offered by TSMC and Intel, which may be a sweet spot for the low-cost edge platforms. Next, we are going to introduce the DNN+Neuro Sim benchmark framework developed by my group. This is an overview of the framework. So the framework is an integration of NeuroSim with Pytorch and Tensorflow. So we can form an end-to-end framework to benchmark different computing memory-based hardware accelerators. Here, the NeuroSim core is a C++ simulator at the circuit level, which is built upon a hierarchy of the chip tile PE subarray with all the necessary peripheral circuitry. And we support the technology nodes from 130 nm down to 7 nm, where the technology parameters are calibrated with the PTM model. From the NeuroSim core, we can report the energy efficiency, throughput, area, and memory utilization. On top of that, we have a Python wrapper to interface with the Pytorch and TensorFlow, where we can define arbitrary deep neural network models and report the inference and training accuracy under the hardware constraints. And we release the source code of the framework at this GitHub link. And we have two versions available. Version 1.2 is for inference, and version 2.1 is for on-chip training. This chart shows the key features of the framework. So in the Python wrapper, we can define the neural network model, and then in the backpropagation stages, we can model the non-ideal effects of the synaptic devices. For example, here we have this weight update behaviors following the blue trajectory for weight increase and red trajectory for the weight decrease. So this is asymmetry in the weight updates. And also we can have the device-to-device variation and cycle-to-cycle variations when we program the devices. All of those may negatively impact the training accuracy. And in the feed-forward process, we care about the data retention of the synaptic devices, especially for the inference. And also we can consider the ADC quantization effect, as the partial sum precision may get reduced when we have the ADC at the edge of the array. So those will impact the inference accuracy. And then on the hardware side, we are going to map the neural network into a chip floor plan like this with multiple tiles. And then we will unroll the real trace activations and kernels into the input vectors and the weight matrix. And then we can perform the real trace-based simulations on the hardware performance, for example, the latency and energy, through a hierarchy of the chip design. We also consider the interconnect routing into the hardware performance estimation. Here we show the benchmark results using the framework for the inference. Firstly, we consider 32 nm node, where most of the non-volatile memories are integrated today. And here we consider the commercially available RRAM, and this specially engineered RRAM, phase-changing memory, and ferroelectric transistors. So compared to the SRAM as the same technology node, generally those emerging non-volatile memories outperform the SRAM in terms of the energy efficiency and throughput. The key attribute is the on-state resistance. So if you look at this particular RRAM with 6 kilo ohm on-state resistance, actually its performance is not that competitive compared to the SRAM with the computing memory. The key is to increase the on-state resistance above 100 kilo ohm, as we demonstrated here in this ferroelectric transistor, which the on-state can be modulated by the gate bias. And then we can compare with the state-of-the-art like 7nm SRAM. If we do the computing in memory, then still the 7nm SRAM achieves the best performance. Then the question is, when the 32nm non-volatile memory can beat 7nm SRAM? The answer is when the edge compute, where the standby is frequent. So in the benchmark results in the previous slides, we assume that the computation is continuous. That means the compute is very intensive. Of course, here the 7nm SRAM will outperform the other technologies because of the benefits of scaling. But for the edge compute, where the standby is frequent, we need to consider this computation versus standby ratio. And you can see here, if this ratio is below 5% of the duty cycle, then the non-volatile memories can actually achieve better energy efficiency than the SRAM. Even the technology node is lagging behind. Now let's consider the on-chip training scenario. Again, we show this benchmark table, but with more device non-ideal effects taken into account. For example, here we consider the nonlinearity, the cycle-to-cycle variations, or the training accuracy. Those are the data extracted from the literature. As you can see that many of the emerging non-volatile memories could not achieve good training accuracy. Only this FE-FET-based design can approach the digital software accuracy. The good attributes here are the relatively small nonlinearity and symmetric updates, and also relatively small cycle-to-cycle variation. If you consider the peak performance on chip, again, the non-volatile memories can outperform the SRAM as a same technology node. And the 7nm SRAM still achieves the best on-chip performance. But the training is very DRAM intensive, as there are many intermediate data we need to save to the DRAM. So if you consider that, overall the system performance is limited by the DRAM access, and the energy efficiency is limited to like TOPS per watt, regardless of the technology we used on chip. So this is still a big challenge for the on-chip training design. So we think edge inference is a more suited application for the computing memory. Then what device property matters for the inference? Here we would argue the multi-level stability of the conductance states is a key parameter for the inference accuracy. So here we consider 4 drift schemes for the conductance states, like all the conductance drift to the maximum, all the conductance drift to the minimum, and they drift to the middle, or they randomly drift. With those 4 schemes, we can run the inference accuracy estimation using the framework, and then report the inference accuracy as a function of time. So here we show that 10% of the conductance drift over 10 years, and we see that the green line here represents the scheme where the drift is random, and it is most robust to the inference accuracy degradation, while the other schemes will quickly degrade the inference accuracy. The other question we want to address is symmetric weight update required for high training accuracy. So this is a problem when we use emerging non-volatile memories for on-chip training. As we know, the device suffers from this non-ideal weight update, where the conductance increase may follow the blue trajectory, and conductance decrease may follow the red trajectory under the identical pulsing scheme. So here we can see that the training accuracy will quickly degrade over the nonlinearity levels from 0 to 8, as we labeled here. We can use this example to illustrate the challenge, assuming that the device may go up the conductance states following a few steps, and then the next step is to reverse the weight update direction. Due to the asymmetry, then the conductance may have a big drop. So statistically speaking, the device may be easier to concentrate the conductance in the middle range. So it's hard for the device to converge at the two ends of the two curves here. To avoid this kind of problem, we propose a weight update rule utilizing the momentum. So here the idea is to determine the weight update step, not only following the current gradient, but also consider the accumulation of the gradients in the past few steps. With the optimized momentum factor beta, we can achieve very good robustness against the nonlinearity under a symmetry. You can see here, even with the nonlinearity level 6, still like 89% of the training accuracy can be maintained for the CIFAR 10 dataset if we use this momentum technique. Next, we will discuss a few key challenges for the computing memory chip design. The first challenge is the ADC overhead. As we see from our prototypes, the ADC consumes significant area and also the power consumption of the total chip. But the ADC requirement is unique for the computing memory. It does not need super high resolution. For example, 3-bit to 6 bits are typically enough for maintaining good inference accuracy. But there are stringent requirements on the area of the ADC. Because the column pitch is very tight, especially in the RRAM-based design, so the ADC may be too large to fit into this column pitch. Therefore, multiple columns may have to share one ADC through the mux. That means we have to use time multiplexing to read out all the columns, so the parallelism is reduced, thus the throughput is suppressed. So here we compare two commonly used ADC for the computing memory. The first one is the Flash ADC, where we have multiple comparators, but with different references. The other one is the SAR ADC, where we only have one comparator, but we dynamically change the reference according to the SAR logic. Here the benchmark shows that the area and the power will exponentially increase with the resolution of the Flash ADC, and the latency will linearly increase with the resolution of the SAR ADC. So overall, the SAR ADC is preferred for like higher precision, for example, more than 4-bit resolution of the ADC due to smaller area and better overall energy. The second challenge is the variations with the analog compute, which can degrade the inference accuracy. The primary variation sources include the cell-to-cell on-state resistance variation and the ADC offset. As we see here, we can use the write and verify technique to tighten the distribution of the RRAM resistance. So this can be minimized by the programming. But the ADC offset is post-manufacturing and cannot be tuned. So here we show the measured ADC output versus the ideal ADC output, and you see the spread out. Although we can fine-tune the references to try to tighten the distribution, still we see the ADC offset is a key parameter that limiting the accuracy for the inference. One potential algorithm-level technique to compensate the ADC offset is to perform the retraining from chip to chip. So here we show the ADC offset pattern from the Monte Carlo simulations. And then after each chip is manufactured, we are going to run the inference on each chip. And then we generate the prediction compared to the true label. Then we can perform the back propagation to fine-tune the weights. So we can adapt the weights to each chip's variation. So here we show the effectiveness of this approach by one epoch retraining. And we see that the accuracy can be significantly recovered, but still cannot approach the software baseline. The third challenge, in particular to the RRAM technology, is the low on-state resistance and high write voltage. If the RRAM resistance is low, for example, a few kilo-ohm for the on-state, there will be a large column current because we sum up multiple rows. and there will be IR drop along the interconnect wire, which may lead to analog readout accuracy loss. And if the unstable resistance is low, we need to support large current current. That means we have to size up the max transistor as edge of the array, which may lead to poor area efficiency, as we see here in our layout. Also, if the RRAM rate voltage is high, for example 3 volts, then we may need to use I/O transistor to deliver this voltage. Then the bit cell size may be large. And also we may spend a lot of area on the level shifter here to convert the voltage from the logic domain to the analog programming voltage domain. So the desired engineering targets for the RRAM technology is to improve the unstable resistance above 100 kilo-ohm and reduce the rate voltage to be logic compatible, less than 1 volt. Lastly, I want to discuss a promising future research direction, which is this monolithic 3D design, which can mitigate some of the challenges we mentioned earlier. So here is a proposal of the monolithic 3D design, where we are going to split the design into 2 tiers. The top tier will have the RRAM array and its closest peripheral circuits, where we have to maintain the high voltage. And then on the bottom tier, into the silicon substrate, we are going to scale the peripheral logic and ADCs into more advanced technology nodes. Here we can open up more space for the ADCs, so we can mitigate the problem of the column pitch matching between the ADC and the RRAM array. And on the right-hand side, we show the mixed-signal design flow into the physical design environment. So here we are going to customly build the analog modules using the Cadence Virtuoso, and then we are going to generate the physical design model parameters in the net file, lib file, and then we are going to perform the whole synthesis using the Inference tool, where we can have the digital logic and the analog custom blocks integrated together. Here is a case study to design a 2.4 megabit RRAM computing memory tile using the design flow in the previous slide. And here is a hierarchy of the design, where we have a RRAM subarray with 128 rows and 128 columns, and then 4x4 of such subarrays will form one PE, and then 3x3 PEs will form one tile. Here we include all the necessary peripheral circuits into each level of the hierarchy, including the switch matrix, mux, level shifters, ADC, shift and add, accumulators, buffers, and so on. This is a physical layout generated by the synthesis tool. The top row shows the 2D baseline design at 14 nanometer load, with a hierarchical view from the subarray to the PE to the tile. And the bottom row shows the monolithic 3D partition, where the logic transistors are placed at the bottom tier at 16 nanometer, while the RRAM array and the mux and level shifter are placed at the top tier at 40 nanometer load. This slide shows the performance benchmark between a 2D design versus a monolithic 3D design. First of all, the chip footprint is significantly reduced by more than 50%. Now we have more space to place the ADC on chip, so the number of ADC is increased by 8 times. That means the throughput is also increased by 8 times. At the same time, the power is increased by 2 times. So overall, the energy efficiency is improved by 4 times. The thermal map here shows that the temperature increase in the 3D design actually is minimal, less than 10 degrees C. This is because in this particular design, the power density is pretty low, only 0.2 watt per millimeter square, which is about 5 times smaller than the typical GPU power density. Therefore, the thermal profile is still manageable in the monolithic 3D design. Alright, let's have a summary of the presentation. First, we think computing memory saves the intermediate data movement thus improve the throughput and energy efficiency of the accelerator. Today's RRAM can be tuned into the multi-level states, possibly by the iterative write and verify. So the inference is still the most suitable and tangible applications of the RRAM technology, which RRAM may hold the advantages over SRAM because of the low leakage and non-volatility for the edge computing. The slight inference accuracy degradation in the end compute is caused by the process variation, in particular the ADC offsets. This may bring the overhead of the retraining from the chip to chip in the testing phase. RRAM-based design still faces the challenges such as the high rate voltage, low on-state resistance, ADC overhead, intermediate state instability, and so on. The DNN+NeuroSim is an integrated framework to benchmark different computing memory technologies, and that is open source to the community. And finally, we believe that the monolithic 3D integration, where we place an RRAM on top of a logic, seems a viable solution to alleviate some of the design challenges, such as the ADC bottleneck. Finally, I'd like to acknowledge my collaborators in the research, including Professor Mengfan Chang from National Tsinghua University, Taiwan, on the SRAM-based design, Professor Jason Seal from Arizona State University on the RRAM-based design, and Professor Sankyu Lin from Georgia Tech on the monolithic 3D-based design. Of course, I'd like to thank all the postdocs and students involved in this research. Then I'd like to thank the generous support from our sponsors, including the National Science Foundation, Semiconductor Research Corporation, including the JUMP and NCORP program, especially the Ascent Center under the JUMP. If you have more questions regarding this presentation, feel free to send me an email at this link and also visit our group website using this link. Thank you. This is the end of the presentation.